everyone in this session. Speaker is Huitzu, and he will talk about dark photons. Did I spell correctly? Okay. She will talk about the dark photons in Weinberg Higgs Photon model as fractional cosmic neutrinos.
So good afternoon, everyone. And first of all, I would like to thank the organizers for the invitation to present my work done with my collaborators at Academia Sinica, King Wong and TC, and dark photons. The motivation for our work is that, as we know that the cosmic microwave background data can be used to infer the effective number of light neutrino spaces. For example, the latest Planck data from last year, combined with WMAP 9-year polarization data and some high multiple experiments, infer an effective effective number of light neutrino species of about 3.36 at a 95% confidence level. If combined with this is consistent with the baryoacoustic oscillation data. So if we include it, it will be even more stringent. This result is firmly consistent with the prediction by the standard scenario with 3 massless active neutrinos of 3.046. The deviation from exact 3 arises from the fact that the neutrinos did not decouple from the thermal bath in the early universe instantaneously. So there seems not to be much room left for an extra light species. However, let me point out to you that there is apparently a tension between current CMB data and other cosmological measurements. For example, if there is a tension on the CMB, the Hubble expansion rate measured by CMB data alone is lower than that inferred by direct measurements of the Hubble expansion rate H0. This tension is found to can be lifted, at least partly, if one allows the effective number of light neutrino species to be larger simultaneously to fit a larger value for H0. As you can see in this plot, which I borrowed from the Planck official paper. So the black and blue curves, this is a posterior distribution for N effective. So as you can see that the blue and black curves prefer lower value closer to the standard prediction, whereas if you were trying to reconcile or compromise with the direct Hubble expansion rates measurement, then N effective would prefer the larger N effective value is preferred. The situation is similar if you want to reconcile the CMB data with the measurements of local cluster abundance measurement. So CMB would prefer a higher, much more power at a small scale than local measurement do. So it is found by those people working at our recent paper that if you include a stereo neutrino, for example, or any light species, and which has a mass, then you can reconcile CMB data and Hubble expansion rates measurement and the cluster measurement, and bring them in a better agreement, as is shown in this confidence plot here. So the result in this work shows that the minimum neutrino model with zero, with no effective contribution to neutrino degrees of freedom, and zero even massless light species is strongly disfavored. So from here we can see that the motivation for having extra light species, or whether this species is massless or massive, depends really on what kind of cosmological data you want to look at. Okay, so among all the candidates for the extra light species, last year, Weinberg has proposed that ghost-on bosons can play this role. The motivation for him was that since the ghost-on bosons are created naturally massless or nearly massless, so very light, and also their characteristic derivative coupling would make them very weakly interacting. So they can decouple from the thermal bath sufficiently early enough so that they don't contribute too much to any effect. Because we want them to contribute just it's like at the 0.5, 0.6 level. Okay, so the requirements on the ghost-on bosons or any other candidates is that they have to decouple from the thermal bath early enough, so that the temperature is lower than that of the neutrinos. The collider signatures and phenomenology have been studied quite in detail and abundantly in many references. So here I mentioned one. With my collaborators, Wei Yikong and TC and Kim Wen, we've also studied astrophysics aspects. Namely, we consider supernova cooling and derive useful, very strong constraints on Weinberg scenario. In this work, however, in Weinberg's original model, he considered a simplest case in that he includes a global U1 symmetry and a complex scalar singlet field to break it spontaneously. And that gives rise to a kind of dark Higgs and ghost-on bosons. In this work, we gauged U1 global symmetry in this U1 symmetry in Weinberg's original model. So in place of the ghost-on boson, we have dark photon instead, which is massive at the spontaneous symmetry breaking as they absorb the ghost-on boson. And its contribution, since it's a massive gauge boson, so its contribution to N effective is 3 times larger. With its 3 polarization states, it's 3 times larger than that of the ghost-on bosons. So this too will give us some very distinct feature of this scenario compared to Weinberg's original model. First, let me briefly remind you how the effective number of light neutrino species is defined. It's characterized, the neutrino contribution to total energy density is defined through this parameter N effective. So here's the neutrino temperature relative to the photon temperature. And from the conservation of entropy per co-moving volume in the universe, this definition can also accommodate any other light species called X here. Its temperature relative to that of the neutrino, after a neutrino completely decoupled from the thermal bath, is dictated by the conservation of entropy per co-moving volume. So H effective here is the effective degrees of freedom for the entropy density, which I will show you in the next plot. So from this, we can easily estimate the contribution of any light species X to N effective. So it depends on whether it's a boson or fermion, and its the internal degrees of freedom, and its temperature to the 4th power. So this is the plot for the previous relation I just mentioned. So this is plot for the dark. This is a contribution of the dark photon to delta N effective, independence of its decoupling temperature, because its temperature relative to a neutrino is fixed by the effective degrees of freedom for the entropy density at its decoupling time. Okay, so the red solid curve is, tells us how much dark photon can contribute to delta N effective, depending on its decoupling temperature. So we see that in order that the dark photon contribution satisfy or does not violate the CMB constraints, or CMB plus other cosmological data constraints, that is about 0.5 or 0.6, then a dark photon has to decouple around 160 MeV in the early universe. We don't know yet how the future data will go, but maybe it has to decouple even earlier or later. But this is interesting. The decoupling temperature is quite close to the QCD phase transition temperature in the early universe, as recently found. As recently confirmed by many lattice QCD calculations at around 150 MeV. So therefore, in considering or deriving the dark photon decoupling criteria, we really have to distinguishing between the two regimes, whether it decouples before the QCD phase transition or after. To use consider different decoupling channels. So here briefly mention our model. So compared to most of the models I heard in this workshop, our model is really quite simple. So just add one U-engaged field here, and to a solar model, and a single complex scalar field, which is singlet here, denoted by this chi to this Lagrangian. So here the potential, the phi here, phi here is the standard model Higgs field, Higgs doublet. So this is the potential for standard model Higgs and this extra complex scalar field. And know that they couple with this coupling constant lambda phi x phi chi, which we'll call the Higgs Photon coupling. And this dictates all the phenomenon in our work. This is the only coupling between the dark photon and the standard model particles. So as you know already very well, so in the unitary gauge, those two scalar fields are in this form with these real fields to HD, which you call the dark Higgs, and the Higgs standard model Higgs field H. And the dark photon becomes massive with a mass given by the hidden gauge coupling and the vacuum expectation value of this dark Higgs. And the dark Higgs and Higgs mix with each other, giving rise to two eigenstates, H1, H2, with mass eigenvalues M1 and M2. The mixing angle is given by this, proportional to the Higgs photon coupling here. So we identify the heavier one with the standard model Higgs boson, with the mass at 125 GeV, and we assume that the dark Higgs has a mass much lighter than the standard model Higgs boson. Just an assumption. So this the mixing angle here can be constrained, for example, by mu anomalous magnetic moment mu g minus 2, and also meson decay. So this is a plot I took from this paper. It shows the chaos decay is not stringent, only in a smaller region. Okay, so here more about our dark photons. Here more about dark photons. So there's at low energies, there's an effective interaction of the through the dark photons with any standard model fermion pairs, just through the dark Higgs mixing. So you can see the interaction is always in combination in this relation of the Higgs photon coupling divided by the mass square the dark Higgs. Of course, through this mixing, the dark Higgs can also couple to standard model H bosons, as you know very well. I should mention here that I think many people will raise the question immediately whether there's a kinetic mixing between the standard model photon and the dark photon. In this work, we assume it to be sufficiently small so that we only consider this Higgs boson coupling. This assumption can be justified when you look at this plot, which I took from this paper. So the vertical line is the kinetic mixing parameter, horizontal line, the dark photon mass. So as you can see, well, in the dark photon mass range we're interested in, which is sub eV, so 0. Something eV here. The kinetic mixing is already constrained very well down to 10 to the minus 12, majorly from some dark photon flux, which from the sun. And this green line is just the projected sensitivity by future experiments, which is not there yet. Anyway, this justifies our assumption. So in this work, our dark photon can be thermally produced by this interaction, and it's long-lived. It's a long-lived particle, because even if you neglect this kinetic mixing term, it cannot decay to anything. While the only decay channel is through this kinetic mixing. And also since our dark photon is very light, there's the only open channel for it to decay through this kinetic mixing is the dark photon decay to 3 standard model photons, which will take the age of the universe. So we can consider it as very long-lived. And so this makes it to be a hot dark matter component. So now that white hot dark matter, because it decouples very early, so at around, we just say around 160 MeV. Well, its mass is just around, it's below eV, so it decouples ultra-relativistically, and still relativistic during structure formation. So our model, I just want to emphasize here that our model is not about dark matter, so just don't want to confuse you. Okay, so we have, in this model, we have then 3 parameters, which are the Higgs photon coupling, the dark photon mass, and also the mass of the dark Higgs. So there are several constraints on those parameters, which, first of all, here I only listed the constraints on the dark photon mass, because the constraint on Higgs photon coupling and on the dark Higgs mass will come from colliders and supernova, and also from the decoupling criteria. So first of all, they're calculating the relic abundance for the dark photon, and it demands that the dark photon mass should not exceed 70 eV in order not to enclose the universe. But you can make this even more stringent. So I think it's well to say that the dark photon has to be in the sub-eV range. And there seems to be a huge hierarchy between the dark photon mass, which is just below eV, and the mass of the dark Higgs boson, which we assume it to be around GeV. So these two are related by the hidden gauge coupling and the dark Higgs self-coupling. How to achieve this hierarchy? One example is found in this work that naturally we would expect that this hidden gauge coupling to be around point something, just like in standard model. But in some string scenarios with very large extra dimension volume, hybrid gauge coupling 10 to -4 or even smaller can be actually generated. Okay, so collider bands this scenario. the most useful constraint is from Higgs standard model Higgs invisible decay width, which is constrained to be a global analysis constrained to be smaller than 20% now. So in this model, the standard model Higgs can only decay to a pair of dark photons or a pair of dark Higgs bosons. So adding this, confronting this with this constraint, we found a bound and the Higgs photocoupling of about 0.01. This is to be confronted with the early universe decoupling criterion, which I'll show in the next plot. Future prospects for collider constraint. So if in the future the ILC will be realized, as this paper estimated, they will achieve a sensitivity to Higgs invisible decay width to about smaller than 0.4 to 0.9%. So it's an improvement from 20% down to 0.4%. So this bound and the Higgs photocoupling can be improved by factor 5 to 7. So this is the best case, or the best scenario in the future. Okay, so now we want to consider the decoupling criterion of the dark photon from the early universe. So as just said, we have to consider two regimes above and below the QCD transition temperature. So above the QCD transition temperature, the dark photon pairs annihilate or produce mainly into those standard model particle pairs like strange quarks, gluon pairs, muon pairs. It's just because Higgs coupling is more effective to those heavier, to those particles. Gluons. Okay. Below the QCD transition temperature, we have instead of the quarks and gluons, we have pions pair, annihilation into pion pairs and muon pairs. Same as here. So just include all these channels and calculate the thermally averaged annihilation cross section times the Miller velocity in order to calculate the annihilation rate and compare with the Hubble expansion rate to determine the decoupling criteria for the dark photons. Skip this. So this is our main result here. So here, the y-axis is plotted the Higgs photocoupling divided by the mass, the dark Higgs mass squared, against the dark photon decoupling temperature from the early universe thermal band. So the red line is from the decoupling criterion. It tells you if, for example, if I want the dark photon to decouple around 160 MeV, is these two parameters, the combination, these two parameters have to be on this point here. So, and this has to be confronted with the collider bond, which is only sensitive to the Higgs photocoupling and not to the dark Higgs mass, because this always drops out in comparison to a standard model Higgs mass. So in order to plot them in the same plot, so I have to assume different values for the dark Higgs mass in this plot. So this gives rise to this magenta lines like collider bonds, assuming dark Higgs mass to be 1 GeV, 2 GeV, and so on. So back to the criterion. Dark photon decouple around 160 MeV would require that the dark Higgs to be lighter than about 2 GeV, 1 point something, not exactly 2, but this is the main result. So the dark Higgs cannot be too heavy, otherwise your Higgs photocoupling must be larger as well in order to stay on this red line. But for lighter dark Higgs, there's no problem. You can always make this Higgs photocoupling lighter in order to satisfy this criteria. If I have zero, okay, perfect. So At the end, I would like to present our supernova bond, which is seem to be comparable to comparative to collider bonds if the dark Higgs mass is lighter than 1 G. So when the dark Higgs mass is about 500 MeV, so this you can expect that the collider constraint would be roughly at the same level as a supernova. Okay, how this supernova bond is obtained. The neutrino burst from the supernova 1987A have been recorded in several terrestrial detectors. So from the observed neutrino burst duration, the standard picture of neutrino cooling is well established. So if you have any other light particles which interact even much weakly than neutrinos, then it will not be trapped in the second phase of neutrino of supernova cooling. So it can lead to more efficient energy loss from the supernova core. So this led to this argument led to this emissivity band derived by Raffelt. It says this is a emissivity, so it's the energy loss rate divided by the energy density at the supernova core, which is this large, which says it cannot exceed that of the standard model neutrinos. And this bond has to be applied at a core temperature of 30 MeV. This bond, the supernova bond, has been applied abundance quite a lot on different particles like axions, Kaluza-Klein gravitons, and particles, and so on, and has been reaffirmed by simulations done by those people. They work on extra dimensions with Kaluza-Klein gravitons. Okay, so in the supernova core, you have neutrons, protons, electrons, and neutrinos. And you have to determine their abundances there. The most efficient production channel for the dark photon is from the so-called nuclear Bremsstrahlung processes in supernova core. And also because we have remember our dark photon has to couple to standard model particles only through the mixing of the dark Higgs with standard model Higgs. So it couples to the heaviest particles. So here I only show those diagrams to sum up. So here you can see that a pair of dark photon, I should replace here with dark photon. This was made for Gilstone bosons. So can be emitted in the collision of no-relativistic collision of neutron or neutron-proton or proton-proton, and be emitted from any of the participating nucleons. And also, since the standard model Higgs particle has an effective coupling to a pair of pions, you can expect emission of dark photon pair from the pion exchange pion lines here. And those channels, those diagrams give the same order contribution to the total energy loss rate. From the vertex, I don't know. You have to have something like pion, Higgs, nucleon vertex. But there will be, even if you have that, there will be subdominant. 1 minute, perfect. I'm at my last slide. So taking into account all these diagrams, you can calculate at the lengthy calculation, you arrive at this result. And what I want to point out to you here is the very strong dependence of the temperature. This comes majorly because remember the the dark photons and also the major contributions that goes on boson mode there. So the dark photons cover with derivative coupling. So there's very strong, already very strong momentum dependence there. And also, since this is a scalar interaction, so if you consider like equal mass and non-relativistic collision, there's a dipole radiation suppression. So we have to, this is already the quadrupole radiation temperature dependence. Okay, however, due to this suppression, the supernova bond is found to be still comparable to collider bond, as I showed in the previous figure here. So just depending on the mass of the dark Higgs. Okay, so that's it.
Are there any questions for the speaker?
So you took around 1 GeV for dark Higgs mass. Is there any particular reason why is there any preference for GeV scale dark Higgs, or it can be arbitrary?
Okay, it can be arbitrary. So actually, the problem is that this is an okay. We consider here in this work only an effective interaction. So you see, we have to have this two mass square in denominator comes from the propagator. So if the mass is closer to the energy scale you consider, like for in supernova, you can use it. Yeah.
More questions? Okay, I have one question. And can you go back to the slide on the collider bonds for the Higgs photon chambers?
This one. Okay.
Okay. If my memory is correct, the Photon has pursued a search for the Higgs decay into 4 muons. So did you check the bond of this search? Because here, if the Higgs is 1 GeV, yes, I suspect that this bond could be stronger compared to the bond from Higgs decay to invisible state. Higgs decay to 4 muons.
So what?
Yeah, because if dark Higgs is 1 GeV, then its branching ratio into 2 muons.
No, the dark Higgs cannot decay to. Yeah, but the decay, I checked, the decay of dark Higgs back to small amount of particle pairs is relatively small.
Very small.
Yeah, it's much smaller than the decay with to this 2 channels. It's about 10 to the -8 or something.
Yeah, I'm talking about the decay of HD.
Yeah. Oh. Yeah, sure, because the dark photon cannot decay. Okay, so HD can only decay to a pair of dark photons.
But there is a mixing between
dark
Higgs and standard model Higgs.
Yeah,
right?
so I can.
So certainly this
I calculate that. So.
Yeah, certainly this can decay to.
Yes, they can. So the branching ratio of dark Higgs boson decay to standard model particle pairs is about 10 to the -8 times of the decay with two dark photon pairs.
What is the reason? Because here I think that
the mixing
is
angle.
so small.
It's just the mixing angle. Okay, I have a plot for the mixing angle. Right? Okay, this is from other people's work. So the mixing angle is already constrained to be 10 to the -5 or something. I square it.
I see. Okay. Thank you. Okay, that thing is